Hi, my name is Shad, and I'm going to be your teacher and guide today for this course on software reverse engineering. So that's the technique of taking code that's already been compiled and reversing it into something that you can manipulate. So that means you might see the source code, or at least you will be able to see the assembly language and then make any modifications or understanding of what the program is doing. So this course is taught in 8 pieces. In part 1, we'll talk about numbering systems. So if you have not seen binary numbers or hexadecimal before, this will give you a great start into how you can understand what a reversed piece of software looks like. Then we'll do some experiences to get you used to the idea of software reverse engineering, the first attempts. Then we'll have a session where we compare the different tools that are popularly available. And of course, we're looking for free tools, but there are commercial ones as well. And then we'll talk about the reading the stack feature. So this is understanding a program as it's running and doing some debugging while it's in action. So that's this video here right now. Binary patching is about taking a piece of software and modifying it, even if you don't have the source code. And so you can patch things to fix errors or to maybe bypass a certain feature like a login screen or a registration screen. Recognizing code patterns will give you a more in-depth advanced feature of how you can see maybe malware and diagnose what it's doing. And then anti-debugging techniques is the ability to take a piece of software who is trying to hide from you. So this is a cybersecurity topic where we are looking at software that knows that you are reverse engineering it and you're trying to avoid that. And then finally, we'll do some fuzzing techniques. So this whole course here is about software reverse engineering. Now, the guides that are going to take us through here are from Dakota State University. So Michael Ham and Andrew Kramer are both the teachers. So let's get started with this section right now on software reverse engineering.
So the main topics that we're going to cover this first session here are going to be some stack memory. So we looked at a little bit of the function prologue, function epilogue, and we're going to look at like what contents live between that now. So to make sure that we're on the same page of how the stack works, what its purpose is, how we interact with it, we'll go through a few slides on that. And then we're actually going to open up some of the tools that Andrew demoed during the last session and start to kind of like analyze and follow this data in those environments too. So it's kind of our mission for that. So when we're interacting with the stack, we're going to see a lot of different instructions to put data into the stack, remove data from that, and those 2 instructions that we see most often are a push and a pop. So when we push data onto the stack in a 32-bit program, we're making 4 bytes worth of data and saving something into that memory location. If it's a 64-bit program, the exact same thing happens. It's just 8 bytes of data instead of 4 bytes. So a good example of where we use the stack is when we create any sort of local variables. So if we were actually to go into our compiler explorer, if you still have that open. So in this example, so this is in the Microsoft compiler. So we see things represented a little bit differently than what you'd see in using GCC. And what I mean by that up here at the top is we have kind of these aliases. So anytime you see $a$, that's going to represent a -4. The importance of that, it's not so much right now, it's just the fact that we're saving these numbers in between that function prologue and the function epilogue. So can someone just remind me what the prologue and epilogue were used for? Yeah, so it saves our return address so we know where to go back to, and it defines where our stack memory is going to be at. And the address of our stack memory happens where we reset the ESP register into EBP. So this push EBP at the top here is saving our return address. Where do we go back to when we're done executing the function? The next line down, we remove the ESP, which is the stack pointer, back into EBP, which is the base pointer, is going to be the top of our memory addresses that we have here. All of the local variables I create, like integer A, B, and C, are going to live at a lower memory address than this base pointer. And so this is where doing that quick math of like hexadecimal numbers in our head becomes a little bit handy, because we can see this is actually showing it to us in decimal. But in a lot of our tools, instead of saying this lives at EBP minus 12, it's going to say EBP minus hex C. So being able to do that subtraction in your head will help you find out where those local variables live a little bit more easily. So within the stack, when we create local variables, they're always going to have a negative offset from that EBP register. Another important thing to know about EBP is during the existence of that stack frame, so as long as that function's being executed, it's never ever going to change. So it's always a reliable place that we can pull an offset from to find something. So if we look at how the stack works a little bit more closely, this would be like a blank stack frame. So if I just called a function in our program, we have to set up and reserve the memory for all those local variables, save the important data to it, and then we can look at how that's actually going to be laid out here. So if my stack memory addresses are in 4-byte increments, what do you suppose this is, a 32 or a 64-bit program? 32-bit, right? The stack works the same way in 64-bit programs. You're just going to see a little bit less data existing on the stack because we want to keep as much in the actual processor registers as we can. So if we were going to set up a stack frame, kind of the way this looks is if we were going to call a function and save all those local variables to it, the first thing that we have at the very top is saving that return address so we know where to go back to. The next thing that we do is establish our new base pointer, and this is that known good value that's never going to change while the stack frame exists, and we save that to the EBP register. After that, when we want to start initializing and saving those integer variables onto the stack, we can use a push instruction that's going to decrement our stack pointer, so basically moving it down to an unallocated place in memory, and then saving the contents of that variable there. So if we had a few different variables, I only did 3 in Compiler Explorer, but as we can see, it's going to keep going down in memory that way. So I happen to use 4 integer variables, and each integer variable is 4 bytes, so they nicely take up a whole memory address themselves. But this could have easily been like an array of integers. We don't know if it's 4 individual things or if it's an array. It could have been a 16-byte character array, stuff like that. But the point is, when we start initializing those values, they're going to be below our EBP address. So I'm hoping there's some opinions in here. I like to ask the great debate, depending on how you were taught, does stack memory grow upwards, or do you draw it in a picture like I did where it goes downwards? I'm more of a stack grows downwards person. So you do it how you think is best, but I do have a reason for it. When we look at a stack frame and stack memory, that base pointer is going to be the highest numeric address of all of the memory in that stack frame. So if my memory address in the stack is, let's say, 1000, everything that I create in that stack frame will be less than address 1000. So for me, the highest number belongs on top, everything goes down. It's the same either way, it's just how do you want to teach it and how do you like to do things. The second reason I bring it up that way is because if you take heap memory into context, heap memory always starts at a low memory address, and everything you use in the heap is going to be at a higher address from that. So the stack and the heap both grow towards each other, so they both can't start at the bottom, they both can't start at the top. It's opposite, right? The way I like to think about this is if you took a spiral-bound notebook and you're going to use that same notebook for 2 different classes, and I know all of our students diligently take notes, so this is a problem we run into, right? But a strategy they could use is take notes for one class starting at the beginning and just write through their notebook normally, and for the second class they'd start on the very last page and start going backwards in their notes. You'd have 2 classes kind of growing towards each other. That's how stack and heap memory work. So the stack is used for things that are known, they're not really changing, they're going to exist in a function. Can anyone tell me what the heap is used for, since we're talking about it here? So it's for dynamic things. Can you give me like a context or like a practical example of what should live on the heap or how you'd use it? For globals, those will actually live in a data section in memory. Yep. Yeah, so if you're allocating dynamic memory, like you don't know the fixed size of something and you may need to allocate more or less, that would be a case where you'd use the heap. Two things to know about the stack and the heap is that the stack in our normal C calling conventions, when we allocate memory to hold those variables, the function prolog gives that memory back to the operating system. So it cleans up all of the memory that it took by itself. If you're doing this with the heap, you have to free that memory back up. Otherwise, that's going to live in heap memory for, I won't say forever, because there's garbage collection routines that eventually come get it, but it's something you have to be aware of. You need to clean that back up yourself. So, my great debate, if we look at all of our memory layouts, we have a few different sections that we haven't talked about yet, but you can kind of see the stack and heap up in the upper bounds of your memory growing towards each other. And then we have a few different memory sections below that. So the text section, and I'm going to kind of generically group the data sections together. But those are two other important areas that we need to look at when we're doing reverse engineering too. So can anyone tell me what the text section of memory is used for? Yeah, all of your like actual assembly instructions live in the text section. Now what's really interesting about the text section is it's an area that holds those instructions, but like every time we launch another copy of our program, that program's going to reference the exact same instructions in there. So what I mean is like if we open up 10 calculators on our computer, the instructions for the calculator don't get put in the text location 10 times. It gets put into that section one time, and that's shared amongst all those different processes. So that memory is used basically just for holding all of our instructions that we have. How about the data sections? So we might actually be able to see this here in Compiler Explorer. If we just add it into our program. So again, this is in the Visual Studio compiler. You can see here that that string hello world actually lives in a different section of memory in that data section. So sometimes if we find interesting things like a global variable or a string or things that we want to manipulate, we're going to have to look outside of that stack memory here a little bit. So stack memory, like we've talked about, can be used for local variables, it can hold return values. It's also used to pass in arguments to a function, because functions do a lot more interesting things if they take an argument with them. The other thing I really want you to know about when we pass functions arguments is that those arguments are going to be a positive offset from EBP. So our local variables are always EBP minus something. If it's a function argument, we can always see it as EBP plus something. So it's good when we're trying to track down data and figure out where it came from to know, is it local? Was it passed to us from something? So let's go ahead and open up our Kali virtual machines. So the first binary file that I want to take a look at is number 7 here. And all this binary file does is creates a few different integer variables and returns. So really this function is doing absolutely nothing. If we had compiled it with optimization turned on, you probably wouldn't see the function prolog or epilogue. It would just be a return, because there's nothing for this function to actually do. But I want to use this one just to get into our disassembler and get into a debugger, and then see how we can use those two tools side by side. And then we'll make this a little bit more interesting after we kind of get those tools started here. So one thing I want you to do is make sure that all of these binary files are executable. When I cloned them from GitHub, I don't think they came in as executable permissions. So if you're in that binaries folder, just do a chmod plus x, and we'll do star.out. So everything in there that's executable, or a binary file, will make it executable. All right, so go ahead and test it as well. Just make sure it actually appears to run. As long as you don't get any output or errors, we'll assume that it's working okay. Then I'll have you open up Ghidra. So at the very top of your Kali virtual machine, you've got the red dragon icon for Ghidra. Go ahead and click on that and we'll open it up. Okay. So that shortcut appears to be broken. So from your terminal, just type in Ghidra and we'll launch it that way. All we're doing so far is we're in our GitHub binaries folder and we just launched Ghidra. We're just going to go through number 7 real quick. Everybody get that opened up. I'll walk you through a few things in Ghidra, just getting a binary loaded up, the steps that we take to start analyzing it, and then we can look at some different examples and things too. When we open up Ghidra, it works in what we call projects. Projects are just a collection of different binary files that you're analyzing. Like Andrew mentioned, with Ghidra, you can do either a standalone project, which is just you as the reverse engineering analyst working, or you can do a team-based project, which they call shared projects, and you can have multiple people going at it at the same time. So before we can actually analyze anything in here, we need to create ourselves a new project. So I'm going to go File, New Project. And here's where you can pick, do you want to work with a team of people? Do you want to do it by yourself? I'm going to go with a non-shared project. And Andrew's actually going to help you guys get a shared project going a little bit later on too. So he's got a server and stuff set up, and we can tackle something as a class here. Project directory is just going to be a folder of all of your Ghidra files, and where does it import the binaries, save the database, those kind of things. So in the project directory, just to make it easy to find, I'm going to just put that right on my desktop. Make a new folder, and I'm going to call this FacDev. You name it whatever you want. It's your art project. So we'll select that, give it a project name. I'm going to choose the exact same thing of FacDev. So the project by itself won't do anything. We have to actually import those binaries too. So you can either go to File, Import, or just hit I on your keyboard. And that'll bring up the dialog there as well. And then browse to your desktop. Go to the Git folder. Go into binaries. And we were looking at number 7, stacklocals.out. Okay, so when you double click on that file to select it, it's going to ask you how you should import it. And this probably looks familiar to what Andrew did with IDA, where it said like, we think it's built by like this compiler, we think it's either a Linux file or a Windows file. It tries to make some assumptions based off of that. Based on this file header, we know that it's a Linux executable file. It's an x86, which means we're working with the 32-bit binary here. So we'll just go ahead and hit OK there. It's going to import it, kind of reads that file structure, sees how the memory and stuff should be laid out. And now we can actually start to analyze it. So when you have it imported, the tool that we use is called the code browser. You can either hit the drag in here or just double click on this file and it'll open it up automatically for you. And then it's going to pull out the assembly from that. So I'll give you guys a couple minutes to get that imported. When it asks, do you want to import this and analyze it, hit yes. You can just leave the defaults and hit analyze, and it'll sit and kind of chew on that for a little bit. But let us know if you get questions or you missed something and we can get you caught up. All right, so it sounds like everybody's kind of got to the right spot here. There's different tools within Ghidra. So typically we're going to do most of our analysis in the code browser, which is what you're looking at right now. Ghidra does have its own debugger built in. I frankly don't have a lot of experience with that debugger. People oftentimes will use more popular ones like GDB. If they're working in Windows, they can use WinDebug or like x64 debug. And you can actually tie Ghidra to some of those different debuggers. So that's kind of the world I live in. I don't know if anyone's had experience with the Ghidra debugger. It doesn't seem very popular, but maybe it's a really powerful tool. Is it hard to get working? That's probably why people just kind of seem to avoid it. Right now what we're looking at is the very top of that file. So we're looking at the file header right now. And you can see based on this file header here, it says this is an ELF32, which is the executable Linux format. And it's a 32-bit binary. So Ghidra can read those file headers and get some context clues about what it's working with. In the Windows world, we won't see ELF. Does anyone know what the file header for Windows would be? Yeah, it'll be PE. So there's just clues like that these programs use to figure out what they're working with. So we don't care so much about the file header. What we want to actually find is our important and interesting functions. So on the left-hand side, you have what's called the symbol tree, and you have a file within that symbol tree that lists all of the different functions that you have. So if you scroll through those functions, you'll eventually find my main function, and go ahead and click on that. And we see a couple of really cool pieces of information here. So on the right-hand side, this is the decompiler view that Ghidra gives you. And I forget, Andrew, did you show the decompiler?
No, I don't think we really
Okay. I couldn't remember if we'd gone into the decompiler here.
discussed it.
So according to Ghidra, this is the source C program that it thinks I wrote, or it's representative of the functionality in that program that I wrote. If I were to open up the actual program, and kind of do a side-by-side, what do you think? How good of a job did it seem to do? Mediocre? What's missing?
It didn't catch initializations.
It didn't show that I actually initialized those variables A, B, C, and D. Right, if you also look at some things here, the variable names came in backwards. Not that that's really critical or super important to the functionality of this program, but it's a reason of why we don't rely specifically on a decompiler. We have to use the decompiler and the disassembler kind of side by side, right? Because that decompiler is not going to paint the whole picture. If it were able to, we probably wouldn't be having a reverse engineering class, right? Dump a program in, see the source code, we're like, we can figure this out.
Quick question.
Yeah.
So would your you in the comment in the source code you had some compiler flags?
Yep.
Were those, I can't remember if those were optimization flags. And I'm just wondering if you lost those initializations when you were compiling due to those flags, and then Ghidra just didn't have that information.
It's a good question. So I compiled this obviously with GCC being a Linux binary. And the question was, if we have the optimization turned on, is that why Ghidra is losing some of the info?
Yeah, like basically the optimization may just not put into the executable file those values. I mean, I don't know.
So actually with this binary, I've completely turned off optimization, yeah.
Okay.
So if you do a -O0, that says give me every line of assembly regardless if it's doing something or not. So I think it's just how the decompiler interpreted that and didn't show us the initialization. I found if those variables actually get used for something, it's a little bit more accurate because it can see that context, but according to this program, they don't really get used. The decompiler didn't pick it up, and we're kind of stuck with that. A couple other things. So we talked about this before. The M32 means we're going to make a 32-bit binary. The -G gives us debug symbols. So when we're teaching students and starting out, if we're not having a huge background in RE, I think it's valuable to give them some debug symbols so that when they're in a program like Ghidra, they can see those friendly function names. So they can see things like main. They don't have to go hunt for that kind of stuff. And it just makes that a little bit easier to start with. Obviously, as we grow that skill set and get into more advanced things like malware, they're probably not going to give you the debug symbols to analyze that piece of malware, right? We make that even more complicated if your code is obfuscated. Now we have to figure out where do things live, where is the context of that. So that's a good question. When we look at this program, if I click on what this thinks is integer D, it's not highlighting where I want it to. It's highlighting the aliases up at the top here. So we can see where these variables are in relation to EBP. And that's one thing that Ghidra does, is it tries to make a friendly alias, which isn't always the most helpful. So every time I see A in that disassembler output, in my mind I'm thinking that's -8 hex. So that means my variable A lives 8 hex below EBP. So being a local variable, right, they're always having that negative offset. So Down here, this says EBP plus A. In real life, that means EBP plus a negative 8 hex. So really EBP minus 8 hex. And right next to that is where we actually have that initialization of saving 539 hex into variable A. And so we talked about converting those different radix at the beginning of class. If I can see something like 539 hex, and I'm thinking this is probably an integer variable, as a human, I don't want to see that in hexadecimal. 539 hex is a meaningless number to me. So part of our job as reverse engineers is to start figuring out what this actually should mean for us as humans and making that a little bit more readable. So if we right click on 539 hex, I won't make you do this math in your head. You can actually go down to the bottom, do convert to an unsigned decimal, and you'll see there that it switches it to the actual decimal number that we want. So I changed 539 hex into the unsigned integer, so it's 1337. Is there a way to globally do that? Yeah, I don't know off the top of my head either. Okay, so like Andrew showed you with IDA Pro, we can add comments into our code as well. And this is something I really try to get my students into. Like, we've probably all played the game of having them write C programs. We're like, comment your code, and they fight you every step of the way. And you're like, just please do it. It's good for you to do. When you get into reverse engineering, it's the same thing. If we figure out how something works or what that piece of data should be, it's good to add comments to it, especially for working as a team, right? If you have a shared project, if you figure stuff out, you should give people an idea of what that was. So I use a lot of end-of-line comments, and so if you just hit the semicolon, it's going to bring up that dialog for you, and you can give it any comment that you want to. Since this program's not really doing much, the comments aren't going to be as impactful, but you can see them there. You can also rename things. So it's going to give very generic names to stuff. We have the debug symbols on, so it might actually pull in some of those names accurately, like A, B, C, and D. But if you knew something was actually changed, if you type the L key, you can apply a new label to it. And so you can just do the rename function label. And instead of B, if I knew this was actually going to be like the user's password or something, like rename that and give that variable some actual context. So when you see that happening again in code, you can follow that a little bit easier. So we've been working in a disassembler. What a disassembler does is it takes that binary file off of the hard drive, opens it up, looks at the memory layout, finds all of those instructions for you, and puts it statically in a view for you. Nothing in this program is running, it's not executing, it's just a static picture of what that program looks like. We know, though, when programs run and they have logic and they're doing different things, sometimes we actually need to follow what that program's doing rather than looking at it statically. Like a good example would be if a program's generating a PIN number and we don't want to do the math to figure out how that PIN number was created, we just want to see the generated PIN number, we can follow that in a different program called a debugger. So we're going to open up a debugger alongside of Ghidra and see if we can track down some of this information side by side. So if we're going to identify like really interesting areas in Ghidra, we can take those memory addresses into our debugger and look at the values when we actually hit those instructions. So in your terminal, if you still have that open, we're going to use GDB. And you can go ahead and launch your program number 7. Okay, so within GDB, if we have those debug symbols, we can still find what memory addresses and things they live at. The way that we do that is we can do an info func, and that's going to find all those different functions in that binary, and then show them to us that way. So at the very top there, we can see that we have that main function. That would be a user-defined function. And right below that in all of the orange, we have things that were imported into this program. So things I didn't write, things nobody else in here wrote, but they were necessary for that program to work. So we'll see things in there like a printf, or just normal C functions that are imported as different like linked objects. We don't really care about those because if they're not modified, if they're using standard libraries, there's nothing for us as a reverse engineer to really care about. We're more focused on those functions that were user defined. So if I want to let this program run until it hits that main function, we can set up a breakpoint on that. And a breakpoint is basically just going to pause the program's execution when we hit that point. So the way we set breakpoints is you can do a couple of different things. You can give it the address of a function. What I like to do is if I have the name of it, is just give it the name of that function. So I'll do a B and then a star, which says translate this into the address, and then main. Okay, so I have a breakpoint there. I'm going to run the program. It's going to go through all of the entry points and things that it needs to do until it hits that main function. Then it's going to pause whatever's happening in there. Okay, if I want to see the actual code that lives there, I can do a disassemble. And it's going to show me all of the different functions that live in that main. So this is the same thing here that we were seeing in Ghidra. Now you may notice this looks a little bit different. If we look, for example, here on this line where we're initializing variable a to be 1337, notice how the instructions are flipped around like they're backwards. So I have move with 539 hex on the left, and then EBP -4 on the right. In Ghidra, the 539 hex or the 1337 is on the right versus the left. So the difference between those things is in Ghidra, we're looking at this in Intel syntax. In GDB, that's the AT&T syntax. Most all the stuff I like to work with is in the Intel syntax. It's just how we teach assembly at DSU. I'm curious, does anyone work in AT&T syntax? Okay. So we're going to eventually want to fix that. I forgot to pre-install a tool on this for you all. That's going to make things a little bit easier to see, but we'll get that sorted out here over the break. But there's one thing I also wanted to point out here while we're in here. Yeah. Do you know it off the top of your head? Like so?
Yep.
Okay. Let me scooch that up so you can see it. Then if you run disassemble again, you should see the view that I want to see anyways. So that looks a little better, right? Okay, we're going to install a different tool on top of GDB that gives us more views and a little bit more insight into what we want to look at. It's called Jeff. I'll have to go find the script to download and install it, but it makes GDB a little bit nicer to work with. But kind of one of the last things I wanted to really show you here is we have a little bit of a mismatch in our memory addresses. So who can remember what section of memory do all of the instructions live in? Like, where's the actual machine code living in memory? Was it the heap, the stack, the data section, or text? Text section, right? So all these instructions that are being executed here live in the text section. And we can see where we initialize variable a happens to be at this memory address. So 56556199. In Ghidra, if I look at the memory address of where it thinks that's happening, it looks a little bit different, right? So it's more useful for me if Ghidra is showing me the same memory addresses as my debugger, because if I find something interesting in code, I can then reference the correct memory address in that debugger directly. So what I need to do is something called rebasing the image that we loaded into Ghidra, and it basically just says, instead of loading it at whatever offset it loaded it into, let's load it a little bit further ahead so it matches what's in GDB. So we have to do a little bit of quick math here, and this is kind of where that all comes into play. And I'm going to need a calculator for this. So if I take 56556199 minus this number here, 11199. Right, so we can take this number here, and this will be our new image base that we want. Right? We'll see if this blows up, and then we'll fix it later. So the way we can do this, if our math and assumptions here are correct, if we go into the memory map, this is where we can adjust where Ghidra thinks it's loading those things at. And so you can see the memory base it wants to load this at is at 10,000. We need this to be much higher. So if you click on the home button next to it and paste in that number, I think that's going to break this. But I think this is going to jump it too far ahead. I don't think this is the real image base. And if I go find my main function again, does it actually match? No, our numbers are off. Okay, we'll circle back to this. So I don't want to leave our last kind of demo as like half broken, didn't really quite work how we thought. So we're gonna fix a couple things that'll make the next steps a little bit easier and find out like why our offset was off a little bit when we tried to rebase that image inside of Ghidra. So the first thing I want you to do is type in this command here in your terminal. So quit out of GDB first, because this is going to install another piece of software called Jeff on top of it. And Jeff just makes that layout of GDB a little bit nicer and then adds in some functionality too that's not quite as obvious in GDB. So go ahead and run this. It'll pull down an install script, get you everything you need, and then we'll go back into GDB and see what's different and then fix our issue that we were having before. So if you run this GDB command just like what we did before, you'll notice things look slightly differently. So instead of saying GDB at the bottom, it says Jeff in red text. But it's going to work almost identical to how GDB did. It's just going to look a lot nicer, and it gives us a few more tools that make some of the stuff a little bit easier. So as a refresher in GDB, the way we listed all of our functions to find out what we want to look at was info func. So the only user-defined function we had was main. So we said B for breakpoint, star, and then main. And the way we executed that binary was just with run. And when you type run here now, you're going to see a few different panes inside of GDB that make things a little bit easier. Okay, so you see a few different things in here. My disassembly looks slightly different. It's a little bit smaller window here in the middle. My font is kind of big on my laptop right now, but right above that, you can see what's on the stack. And above that, you can see what's in the registers. So those are the main windows that we typically want to look at when we're running in a debugger, because that's where our interesting information is going to live at. So the one thing that we're trying to do, though, is make what we see in GDB match what's in Ghidra. And that's where we were off by like 10,000 when we tried to rebase that image. So, right, we see where our main function lives at. We see those memory addresses there on the left. What we needed to find was the actual image base loaded in GDB. So a way that we can do that is if this is running and paused by the debugger, is if you type in VM map. This will find you all of those memory address, or the different addresses of the memory sections here in GDB. So at the very top here, this address that we have, 565555000, should actually be our image base. So this is the number that we wanted to put into Ghidra. So if you were to copy that number or write it down, and then go back into your Ghidra code browser, the button we had clicked was memory map. And then over here in the right hand side we have that little house button. And if you paste in that number that you copied out of GDB, then Ghidra should match what we see in GDB. So we were off by 10,000 before. The previous base that we came up with was 5654 5000. And as some of you guys pointed out, it's because Ghidra started us at 10,000 to begin with, so our math was just off a little bit. But if you hit OK here, close that memory map, and look at your main function, all of those memory addresses in the left-hand side there should match exactly what you're seeing in GDB. So now we can start to use those two tools side by side. It's just easier to look at things in Ghidra, find out where you need to be in GDB, and then set your breakpoints at those addresses. So we'll go through a little bit more of that here with a little bit more complex example where we actually want to pull some interesting information out. So to kind of wrap up the last session, we've got a few different things that I want to cover. First thing is going to be viewing information live in the stack using GDB. If we can get that down, it opens up some more fun reversing challenges where I do have some sample programs where we generate pin numbers and do all sorts of crazy stuff that you just have to see happen in memory so you don't have to figure out the math. So I want to show some examples of what that looks like. After that, Andrew's going to do some binary patching. So we introduce program logic or things that we want to change in a binary. That's going to make things a little bit more interesting too. And then we'll give you some more time at the very end to work on some additional CTF challenges. One thing I want you to be thinking about a little bit between now and the end of the day is any student topics that you want us to cover tomorrow. So if there's things that you're like, I really want to see this happen, or ideas for using in your classroom, anything you want us to cover, we'll take some ideas down tonight, and then I'll think about a little bit, see what we can pull together, and then spend a session tomorrow talking about specifically what you're all interested in. So you can give us a little bit of homework tonight, and that'll be fine. Sound like a plan? All right, cool. So what I've done is opened up our next program that we're going to look at. This is program number 8. You don't have to do anything with it. You don't have to open it up right now. I just want you to take a look at the source code, think about what's happening here, and then either on a piece of paper or in a notepad on your computer, I want you to write down what this program is going to print out. Everyone has to write something down. So you gotta commit to an answer. Otherwise everyone just sits there and waits for me to say the answer. All right, do we all have a guess what we think is gonna happen here?
Right.
I need 5 different volunteers to tell me what this is going to print out.
3 big negative numbers.
3 large negative numbers, okay?
All those zeros.
All zeros,
I'll go negative, positive, positive.
okay? Are these any specific numbers or
It's just I wanted 3 stack addresses.
just junk? You say
Or C's like junk.
there's junk, all C's? I need one more. Okay. Do you know what it's going to look like or what kind of numbers that might be represented as? Okay, so just a bunch of numbers. So we have a few different answers. Negative numbers, zeros, random numbers, all C's, things like that. And we're going to track it down and see if we can actually figure out what specifically is going to get printed out here. So I don't want you to run the binary because it ruins the surprise. It's more fun to actually look at this in the debugger and see specifically what's going to happen here. So what we're going to do then is open this up in, we can just go right into GDB for this one. There's not much for us to look at in Ghidra since we just saw the source code here. So we'll just go straight into GDB for this and then take it apart and see what we find. So again, to run that, we're going to go GDB. This is number 8. And once we get inside of GDB, I want you to list those user-defined functions again. So if we do info func, we can see the nice friendly function names I gave all of you with those debug symbols. Tomorrow we'll strip away the debug symbols and make you actually find out where things are. So it's like a valid thing that we're going to see with real applications. But for now, we're just learning the tools, so we're going to leave some of those helpers in there. And you can see that I've got 3 different functions within there. Just for good practice, let's set a breakpoint on all 3 of those. So I'm going to do a B on star F1, F2, and main. So at the top of all these functions, the program's going to pause and we can start to look at what's actually in memory at that point. When you've got those 3 breakpoints set, you can do an info break just to see where they're listed at. So if we wanted to keep breakpoints but later like disable them for some reason or another, like let's say for instance I didn't care about breakpoint 2 anymore, we can do a disable 2. And then if I run info break again, that one would be skipped. So it's handy as you're starting to peel back the layers of what you're trying to work on to set those breakpoints, maybe keep them around, but have the option to turn them on or off. To enable them, just enable then whatever number you had disabled there. And they should be all there. Okay, go ahead and run that program, and it's of course going to bring us to the main function that we have. And we don't really care about what's happening in the main function, right? All it's doing is calling function 1 and function 2. So if I don't want to step through and walk through all those different instructions in main, I can just type continue, or C for short, and that's going to run that program until we hit the next breakpoint in there. Okay, so when we look at function 1, is anything interesting happening in here? Is this where our printf is? Yeah, right, this is the function that we want to be at. We can see it down here in that decompiler view. This normally wouldn't be here if we didn't have those debug symbols and the source code, but since we have both, you can see that. Right above it is the assembly output for that. If I want to see just the assembly, we can do a ctx. I think code should show us. That only shows me like the 10 lines if you just do disassemble. There you can see the disassembly of that whole function there. Okay, what do these first few lines that I have highlighted look like to you? What part of the coding structures have we talked about today that happens at the top of every function we run? Prologue, right? So this is setting up that stack memory. It's where all of our variables live. Right below that, we see variables being pushed onto the stack at a negative offset from EBP. So can we assume those are local variables or arguments? Locals, right? Because every time we see EBP minus a number, that's going to be a local variable. We then do a load address from a different section in memory. That gets saved into our EDX register, which is one of those general purpose registers we can use for whatever. And lastly, that gets pushed onto the stack. So when we're pushing things onto the stack, those are typically going to be carried as arguments to a different function. In this case, that different function that they're arguments to is going to be that printf function. So printf looks a little bit weird. I didn't write that. You'll notice it says printf at PLT, and that's because of the way that this binary was linked. So this is a dynamically linked library, meaning it has to reference printf from the system itself. We talked a little bit about static and dynamic linking at the start of class, so just to kind of show you what that would look like. So I want to know what printf is going to print before it actually executes that, and we can make a prediction on what that's going to look like. So what I might want to do is just set a breakpoint right before printf, and then we can look at the values of all those things that got pushed onto the stack and see what that should be printing out. So a couple of different ways we can do that. We can either pass in the memory address of where we want to set a breakpoint at, or we can use these numbers in that second column where I have plus 35, and that's like kind of an offset that we can use here as well. And that's typically how I like to do it. It's just less typing for me. So I'll set a breakpoint on star main plus 35. And you can see here it translates that into the actual memory address, and it should set a breakpoint there. So go ahead and take a minute, get that breakpoint set. Yeah. Oh, that's a good observation. I messed that up because we're not in the main function anymore, are we? That should have been F1 plus 35. I wish I could say that's the second test of the day, but I just screwed that up, so no bonus points. So we can type continue, and that's going to run through the program until we hit that second breakpoint. Another thing you should be aware of when we're in a debugger is you can step line by line by line and see what's happening each step of the way. So if you didn't want to jump and skip a bunch of code, you want to take a little bit more granular approach. You can do an SI for a single instruction step. And that's just going to move you down one line in that assembly code. If you type SI again, it's going to move you down one line, or when you hit enter, it just repeats the last command you typed. So if you're kind of watching that top pane there, it's just going line by line by line by line. I'm going to type continue, skip down to our breakpoint that we wanted. And I think I went too far because the program closed. So if you do that and go too far past all of your breakpoints, you can just type run again. It's going to keep all those breakpoints that you'd previously set. So if I type continue, I don't think I'm in the right spot, because now my program's throwing a seg fault. Mine's blowing up, presumably, because I still have that incorrect breakpoint I set on main plus 35, which is not what we wanted. So good example here, if you need to delete a breakpoint, just type delete breakpoint number. Now we should be okay. So trying this again, I'm going to rerun the program without that breakpoint that shouldn't be there. We'll hit continue, and now I'm back into my function 1, which is where our printf is. Continue again, and I've now entered into that printf. Now, is there much value in me actually debugging printf? Probably not, right? Because we didn't write that code, there's no point for me really to be inside of there. So I actually want to set a breakpoint before we get into printf, and that we can see what arguments are being passed to it. So let's rerun this one more time here. So we set our breakpoint just a little too far. So I'm in the main function. I'm going to do a continue again to get back to my function f1. And I'm going to set a breakpoint at the previous line to that. So we'll set it at f1 plus 33. So if we do a b star f1 plus 33, and continue to that breakpoint, now you can see above here, we're right before that called printf. So what I'm trying to do is look at the arguments that are getting passed into printf and see if we can predict what numbers are going to get printed out from that. So if I disassemble this again, we can actually inspect what lives at those memory addresses when they're getting pushed onto the stack. And that should give me some insight into how those arguments are going to get passed into printf. Now, one thing I want you to know is when we push arguments onto the stack, they get pushed in reverse order. So if I were to look at the source code here, the format string of printf is actually the first argument that this function takes. When we push it onto the stack, it's actually going to be the last thing that gets pushed onto the stack. Because as we take things back off the stack, we have to go from the top and keep peeling them back off. Which is why some people like to say the stack goes upwards. So you're taking stuff off the top, right? Either way. Okay, so when we look at this, the last thing that got pushed onto the stack was EDX. So what do you suppose that's going to represent?
It's going to be the address to string.
Good, yeah, it should be the address to our string. If we want to inspect that and actually verify it, I can do X for examine. We can give it the format we want it to be in. So if I do /s, that says print this out as a string. And then what do you actually want to print out? In this case, I want to print out whatever was in EDX. And there we go. Should be the string that we were looking at. We can kind of keep going up the stack as well for that. So if I were to look at what was in EBP minus hex C, this isn't going to be a string anymore, right? This should be an integer value A, B, or C. So we could do x/xw, so printing out 4 bytes of hex at EBP minus hex C. So that's the hex value. If I wanted to see that in decimal, we can just change that to /d. Right, and so that should be one of the numbers that would potentially get printed out onto the stack. And we kind of keep just working backwards with that as well. So instead of minus hex C, we can do minus hex 10. That's another number that's probably going to get printed out since that's being passed in as an argument. If we keep working our way back, we have hex 14. That'd be another number that's going to get passed into printf.
So can you explain where these numbers are coming from?
Yeah, so that's the good question, right? So some of us, when we started out, said we're going to get random junk garbage numbers, which these look like, right? They don't look very meaningful. Some people said 0, and some people said some different things in there. These numbers are just coming from whatever was left in stack memory. So somewhere along the lines, our operating system used those memory addresses for something and didn't zero those values out, right? Because that's an expensive operation to do in memory. So it just left whatever contents were in there, and hopefully something will eventually override it. So it's kind of like stack residue is what I refer to it as, is just things that were left in there. To us in this context, they don't have meaning, but somewhere along the lines, the operating system needed that memory. So basically, if we disabled our other breakpoints and we look for what gets printed out, we should see that these 3 numbers at the bottom here will get printed out. So I'm going to do that. I'm going to go just look at my breakpoints again. And I'm going to disable 5 and 6 and 3. So basically all the other breakpoints that I had from this point till the program's done running. And we'll just continue the program and see what numbers actually get printed out. So I have to kind of scroll back up to get past all of the GDB output, but our printf statement executed, and do these numbers look familiar to you? All right, they're the exact numbers that we took out of that. So this is where using a debugger versus a disassembler can be a little bit more useful sometimes. If we want to know like what's really going to be executed at runtime, or what's going to be in memory, or in a variable, or in a register, this is a way that we can do that without having to calculate it ourselves.